Welcome to the Game of Drones, a 4-part podcast series covering every aspect of drones and warfare.
This podcast series aims to give people with some knowledge of physics a deeper understanding of why this discipline is so important to warfare. This is a topic that has relevance at every point in history, so we believe it is important that we understand the impact physics developments, such as drones, have in past and present issues.
From the early use of drones and their current use in Ukraine to the future of AI and drones, the next 4 episodes will give you a comprehensive understanding of the world of drones. Today, I'm joined by Inez, who's first going to tell us about the history of drones. Over to you, Inez.
Thanks for having me. So, we all know about the heavy use of drones in current conflicts, but to understand the need for their existence a bit better, we will have a look first at the introduction and developments of aviation and warfare throughout history. Although the first practical aircraft was produced in the form of hot air balloons in 1783, it wasn't until the end of the 19th century that the use of aviation in warfare truly began. In 1903, brothers Wilbur and Orville Wright were the first to make a powered, sustained and controlled flight in an airplane, a feat soon after which they received a military contract from the USA government, who requested an aircraft capable of carrying 2 people at a speed of 65 kilometers an hour for at least 200 kilometers. Only a few years later, in 1910, arms were first included on airplanes. The first weapon installed on an airplane came in the form of machine guns. At the same time, bombing techniques also evolved. These 2 ways of combat were first used on a large scale during World War I, commencing in 1914. The conflict introduced fighters, bombers, and all other sorts of combat airplanes. In the mind of high-standing army officials, such vehicles would allow to prevent the horrors of trench warfare. The main airship used during this war were Zeppelins, which was a type of aircraft that isn't really highly utilized anymore. They were rigid, long airships, mainly used by the Germans to conduct bombing raids. But they had one main flaw, which was their facility to be set on fire, making them inefficient. Later, during World War I still, military powers realized the obvious advantage airspace above the battlefield provided, leading to heavy investment into fighter airplane development. At first, most rotary radial engines, which is a type of engine that consists of cylinders arranged around a sort of wheel like spikes, and where the whole engine spins around the center as it runs, were used in fighters. They were considered powerful in relation to their weight, but their large frontal surface area introduced a lot of drag that affected the pilot's ability to control the aircraft. Throughout the war, France and Britain focused on improving this issue, resulting in fighters being able to reach up to 188 km per hour by 1918. This was an improvement of over 100 km per hour since the start. Now let's look at the interwar period, which was between 1918 and 1939. It was a time which brought a complete transformation to military aviation. Retractable landing gear, all-metal fuselage, which is the main body of the airplane, and engines with a horsepower of over 1,000 allowed planes to reach up to 560 km per hour. Following this, we have the next major conflict, which was World War II, which brought developments to aerial vehicles, which reaffirmed the superiority over battlefield combat. Something we now refer to as the jet engine era came due to the realization from some engineers that soon speeds would be able to exceed the current capabilities of engines. This was the result of a combination of aerodynamic improvements and the understanding of shock waves, both being concepts which affected aircraft performance dramatically. This era introduced a new aircraft speed concept, the Mach scale. This compares the speed of an object to the speed of sound. So for example, Mach 1 indicates that something is moving at the same speed as sound, Mach 2 means that it's moving at twice the speed of sound, and so on. At first, jet engines were limited by high fuel consumption and many other issues. But all of this was actually resolved during World War II to allow aircraft to reach speeds well past Mach 1 by the end of it. However, this wasn't enough for big military powers. The endless pursuit of aviation vehicles that lowered the financial and the human cost for countries eventually led to the development of unmanned aerial vehicles, commonly referred to as UAVs. The first pilotless vehicles were developed during World War I by the United Kingdom and the USA. Britain's aerial target was a small radio-controlled aircraft, and it was first tested in 1917. And the USA's aerial torpedo, which is also known as the Kettering bug, first flew in 1918. Although these were promising developments, neither country actually used them during the war. In the interwar period, the UK produced several more radio-controlled aircraft, which they use as targets. Although not all UAVs can be considered drones, as we will explore later in this episode, these particular aircraft are believed to have given origin to the term drone. These aircraft were commonly known as remotely piloted vehicles, which we commonly refer to as RPVs, and they were small, inexpensive, and expendable. In fact, countries weren't actually concerned enough about recovery of aircraft until after World War II, where most sophisticated recovery systems were developed. 10 years after the end of World War II came the Vietnam War, a conflict which was the first large-scale deployment of UAVs and the expansion of drone use to many tasks, from being decoys to leading psychological operations. This was the first introduction of photographic reconnaissance of RPVs, a technique which allowed countries to map enemy territory without having to actually enter it with soldiers. A good example of UAV developed for this specific task is the AQM-34 Firebee, which is a turbojet-powered vehicle that travels at speeds lower than sound, but is a third of the size of a jet fighter, a feature which allows it to penetrate heavily defended areas. In the 1980s, these type of spy RPVs improved thanks to the development of avionics, sensors, and precision munition release. The biggest improvement was the introduction of small, high-resolution cameras, which could be remotely controlled. This drastically improved aerodynamics and efficiency in drones. Further, the creation of Global Positioning System, which we call GPS, and is now implemented in our everyday lives through our phones and cars, amongst other uses, allowed military personnel to obtain precise location information for the drones. We can now turn a page to the 21st century, where the US Air Force and the CIA were the first to successfully fit UAVs with missiles. This was the first introduction of armed drones and allowed pilots to control their aircraft from the other side of the world. Over the past 20 years, the US has taken the lead in UAV development, a concept that was heavily invested in during the Obama presidency. However, as we will explore later in this podcast series, the Ukraine war will really go down in history as the conflict that made the use of UAVs a frontline staple.
Thank you very much, Inez. Let's have a look now at the details. How do drones work? What's the maths and physics behind them? To answer these questions, we'll welcome our second guest today, Thomas Jenkins.
Now, as we have heard from Inez, the history of drones and aircraft goes back a long way. But what do we mean by a drone anyway? In the context of this series, we are looking at the warfare in Ukraine, so we will call a multi-rotor, variable input, vertical takeoff and landing, remotely piloted vehicle a drone, specifically a quadcopter. These drones can vary all the way from nano size, that's less than 30 millimeters, all the way to the large class of over 2 meters. The majority of drones used in Ukraine for warfare sit in the medium to large categories. Now, I'm going to assume that you already know a bit of physics, and using Newton's laws of motion, we can derive how a quadcopter is going to fly. Each of the 4 rotors on the corner of our drone produces lift by spinning rapidly, forcing air downwards. In spinning, they also have a torque, which can cause the drone to rotate. This is very important in drone design. So, let's just assume that the rotors rotated in the same direction to see the effect of this torque. At the moment, we just care about the fact that they are rotating and not about the thrust they're producing. Like in a helicopter without a tail, if a drone were built like this, it would begin to spiral out of control. Because the drone body is able to freely rotate, it has a reactional torque to cancel out the combined angular momentums of the rotors, and hence the drone spins. Instead, rotors spinning in opposite directions are placed at diagonally opposite corners of the body. This means that the torques cancel each other out, and the drone won't spiral out of control. For our drone to hover, its weight must equal the force produced by the rotors, following Newton's second law. Let's set the thrust to that so that our drone is now hovering. Making it move up and down now is very easy. By changing the force that the rotors provide, the drone will either accelerate upwards or downwards by increasing or decreasing the force, respectively, according to Newton's first and second laws. Since the drone has 4-fold rotational symmetry, I'll only talk about how a drone translates in the forward direction. The rest will just follow the same process, just in a different direction. Right now, the drone is providing a vertical force from the motors, with no horizontal component. Once again, using Newton's first and second laws, we must provide a force in the horizontal direction to get the drone to move from being at rest. By increasing the force produced by the back, also known as the aft motors, unbalanced forces on the drone induce a torque, causing it to rotate forwards. By resolving the forces into vertical and horizontal components, a component of the force from the rotors is now directed horizontally, and the drone will accelerate forward. Both aft motors are now rotating faster, but equally in opposite directions, and the reaction torque still adds to be zero, so the drone won't spiral out of control. When in this downward tilted position, to keep the drone in level flight, the overall thrust must be increased so that the vertically resolved component still equals the weight of the drone. Finally, to achieve the full 6 degrees of freedom, the drone needs to be able to roll. Rolling is done by using the reactional torque that was so vitally important before to cancel out. In spinning diagonally opposite rotors faster than the other pair, a reactional torque is induced and the drone will roll. But how do rotors produce a force? In order to fully understand this, we'd need to understand fluid dynamics, where the full derivation for this is quite involved and it doesn't have an analytic solution. We'll use a simpler model that remains a good approximation. In short, air is pushed down by the blades, which are angled such that they can scoop air and force it away as they rotate. Crucially, how fast the blades spin and the angle at which they are to the horizontal are important. The vast majority of drones have blades angled at a fixed 45 degrees. So our only way to control how much force a blade produces is by spinning it at a higher or lower angular frequency. The force due to drag is proportional to the squared angular frequency. Thus, spinning the blades faster produces more force due to more air being pushed down. We're going to come back to rotor design in later episodes, but this time in the context of the war. In order to rotate these rotors, a brushless motor is used for best efficiency. A series of windings of copper form solenoids surrounding an axle facing inwards, with a series of magnets placed onto the edge of a freely rotating axle in the centre. It's forced to rotate by inducing a current in the solenoids, causing mutual repulsion by the magnet and solenoids, turning the axle and the rotors. For example, a 3-phase brushless motor has 6 symmetrically placed solenoids, but at any one time only 2 of them are repelling the magnets on the axle at once. To control these, we use an electronic control system. It can provide a variable current and voltage to the motors, inducing a magnetic field due to Faraday's law. This in turn is connected to a communication system so that we can control the angular frequency of the motor and rotors. For example, we can use fiber optics to control our drones, although radio and AI-controlled drones are also in use, and we'll be hearing much more about these later on. For now, we'll focus on the fiber optic controllers. It works by sending a modulated light signal down a thin, usually glass fiber, which acts as a waveguide. It's assumed that the cables in Ukraine are not made of glass, and that they are made of some kind of plastic, as these are much easily manufactured, and we'll come back to these in later episodes as well. They work by bouncing the signal off the optical wall of the fiber due to the differences in refractive indices of air and the fiber, where the latter has a greater refractive index. It's actually the exact same principle as when you see a reflection in a glass window. The signal is sent in at a greater angle than the critical angle. So instead of some of the light being reflected, like in the glass window, all of it is reflected. Some drones use over 20-kilometre long spools of cable connecting to the control station the drone pilot is operating from. Much of the details are classified. However, from conventions used in fibre optic communications, we can assume the modulated signals are sent down in 2 different wavelengths, usually 1310 nanometers and 1550 nanometers. And these wavelengths are chosen due to their low absorbance of the fibre at these wavelengths.
Thank you very much, Thomas and Inez. In the next episode, we'll look at how we counter drones and the science behind stopping them. That's all today. Thanks for listening.